In this video, we're going to be looking at something called exact differential equations. These are just another class of differential equations like linear first order or separable or autonomous. But these differential equations require that we remember a little bit about something called implicit differentiation. And specifically, we need to know about implicit differentiation from Calculus 3, so with multivariable functions. I'll go over that in a minute because some of you may not have had Calculus 3, and so you'll need a little bit of an introduction to that. But first, let me just start with a really quick review of what it means to differentiate implicitly. Here's an equation that is written with the x and y variables both on the same side. Now, this one we could rewrite as y equals negative x plus 7, and then the derivative of y with respect to x would simply be negative 1. But we don't have to, and sometimes we can't rewrite the equation so that the y is isolated on one side of the equation. This one can be rewritten, but they can't all be rewritten. So let's take a look at what we would do with this equation if we couldn't do that. What I'm going to do is I'm going to take each term in turn and differentiate it using the sum and difference rule for differentiation, that the derivative of a sum or difference is just the sum or difference of the derivatives of those terms. So what I'm going to do here is essentially take the derivative with respect to x of x plus the derivative with respect to x of y equals the derivative with respect to x of 7. And for the first term, that's easy because that's just 1. The last term is also easy. The derivative with respect to anything of a constant is 0. The middle term, though, is a little different. We have the derivative of y with respect to x. Well, when we rewrote it this way, y was the name of the function when we differentiated the entire function with respect to the independent variable. So what I'm really doing here is saying the derivative of this thing right here, which turns out to be all of this down here. So what I'm going to do is rethink of this as the derivative of y with respect to x. I can write it that way, or in a lot of cases we see this written as just y prime. And then if I subtract 1 from both sides, I get y prime or dy dx, depending on which form you left it in, equals negative 1. And that's exactly what I got over here. So that's essentially what implicit differentiation is. I had a very simple term here when I took the derivative of this. I literally took the derivative of it, thinking of it as a variable, and then remembering it is a variable. It's thinking of it as an independent variable, but remembering that this is actually a function of x. And so when I take its derivative, I have to take it, the derivative with respect to x is the derivative of this entire function times the derivative of the inside function, as it were, using the chain rule, right? So let me do another example that's a little bit more involved in this, just as a quick review. Okay, this is an expression or an equation that we can't solve explicitly for y. So if I want to take the derivative of this thing with respect to x, I'll need to take the derivative with respect to x of each term, the derivative with respect to x of, I'll put these in parentheses, of this next term, and so on. Now, we don't normally bother to write this out. I've just done this kind of as a reminder that we are allowed to do differentiation this way, right? We are just taking the derivative of each independent term, each individual term. When I take the derivative of the first term, I just get 2x. Because I'm differentiating with respect to x, and there are only x's in that term, so it's just a so-called normal differentiation. My next term, though, has a y in it. So what I'm going to do here is treat this like a product. My pointer. This is the product of 2x squared and y. So imagine, I guess I'll just put one in there, put a little dot in there to represent product. And I'm going to use the product rule. The product rule says the derivative of a product is the first factor times the derivative of the second factor, so I'm going to take the derivative of y with respect to x, plus the second factor times the derivative of the first, and here I can just write 4x. So by doing this, I've ended up in this term. First of all, let me highlight this. This first term just differentiates like this. The second term, when I take the derivative of this thing, I get two terms out of it because I'm using the product rule. All right, so that's one thing to notice. Another is that I have the derivative of y in here. Now, if you're working on these and you've done these before and you're comfortable with doing it, and you just want to write dy dx or even y prime, that's absolutely fine. That's actually how I do it. So if I were writing this, I would write 2x plus, I'd think to myself, the entire first factor times the derivative of the second. So I'd write 2x squared. The derivative of y with respect to x is y prime, plus the second y times the derivative of the first. That's 4x, and then there's my y. So that's how I would do it. But as I'm refreshing what's actually happening here, I've actually written out the dy dx, or the ddx of y. Okay, for my next term, I'm going to, let's see, I have a product here also. So let me put a dot in here to represent where I'm going to split up my factors. And I have, I'm back on this line here now. The derivative of, so the first factor, 3x, times the derivative of the second. Now I've got y squared. So I need to take the derivative of y squared. If it was with respect to y, that would just be 2y, but it's not. It's the derivative of y squared with respect to x. So I have to consider that y is a function of x, and using the chain rule, I also then have to multiply this by dy dx, or y prime. I think I will write that in this line as dy dx. Okay, that's the first times the derivative of the second, plus the second, y squared, times the derivative of the first, which is 3x, so the derivative is 3. And that is, let's see, I'll use a different color here. This term here now also produces two terms because it's a product. Now this next one is also a product, but we know from the product rule that the first times the derivative of the second times the derivative of the first. When I take the derivative of the first factor there, I'm just going to get 0, which is why we're allowed just to pull the constant out front and take the derivative of what's left. So I'm going to get, for the derivative of this term, 6 times the derivative of y cubed with respect to x. If it was with respect to y, I would just get 3y squared, but it's not. It's with respect to x, sorry, dy with respect. I completely messed that up. Let's just start over. The derivative of y with respect to x. And finally, on the right-hand side here, I have the derivative of constant, which is 0. If I tidy this up, as I started to do in this line right here, I'm going to get 6xy y prime plus 3y squared plus 63. No, that was 6 times, wasn't it? So that's going to be 18y squared y prime, and that equals 0. Well, that's the implicit differentiation, as it were, but I still don't have a function that is the derivative of y with respect to x. So I need to find a way to isolate my dy dx's, or in the case of this last line that I have here, y prime, because remember that y prime is, well, I'll just say it's equivalent to dy dx, right? So for abbreviated writing purposes in this line, I've used y prime, whereas perhaps a more accurate way to write this derivative is dy dx, because it tells me not only, like y prime tells me what the dependent variable is, but it doesn't tell me what the independent variable was. Here I can see that I've been differentiating the function y with respect to the independent variable x. So this is it gives me more information. This is just easier to write. So in context, I can see that these are the same. You just have to be careful when you write this, that your reader understands what you're actually talking about. So since I need to solve for y prime, it seems to make sense that I would need to isolate y prime. So what I'm going to do is collect all of my y prime terms. Notice that I can't square this here. It's not y prime times y prime, and it's not y times y. It's y times y prime. They're different. So I have to leave that just as it is. And then I have another term that has a y prime in it. That's 18y squared y prime. And at the same time, I'm being lazy now, and I'm assuming that you already know how to do all of this. So I'm also taking some shortcuts. I'm going to subtract from the left-hand side, well, from both sides, any term that does not have a y prime in it. So I'm going to get my 2x. It's going to be subtracted from the left-hand side and subtracted from 0. 4xy is subtracted from both sides. And 3y squared is subtracted from both sides. So now I have that. And the point in doing this is that now I can factor out that y prime. So y prime times 2x squared plus 6xy plus 18y squared is equal to the right-hand side. And now I can divide both sides by 2x squared plus 6xy plus 18y squared. And I have y prime is equal to, I'm going to write this as negative, and then 2x plus 4xy plus 3y squared all over 2x squared plus 6xy plus 18y squared. And that is how you do implicit differentiation. When you cannot solve your original equation for y so that you can differentiate it explicitly, you differentiate term by term, treating y as a function of x and using the chain rule. That's really all that is. In this case, this happens to be the answer. This is my dy dx. Now let's take a look at what happens when we have a function of multiple variables. Now it sort of looks like this is a function of multiple variables, right? I have x's and y's in here. But if I could have solved this for y, I would have, I'll put this down here, it's not part of the problem, I would have y equals something with a bunch of x's in it, right? And so we say that this is a function of one variable. Yeah, there are two variables here, but this is the important one. This is the input variable. I'm going to do a bunch of stuff to x, and whatever I'm told to do to x, that series of operations, that's what we call y, right? Whatever x is, you do the same thing over and over to it, and when you're done doing those things, it spits out another number, and that's the number y. A function of a function of two variables, we might say, was something that looked like this, something with a bunch of x's and y's in it. And when you do things to both x and y, things that are defined by the function, like this one up here might be y, oh, sorry, wrong pen, y equals x squared, right? You do a bunch, you pick a bunch of x's, you square each one, and the result for each different x is a different y, mostly. With a function like this, we call this a function of two variables. It's two input variables. That function might be defined as something like, let me erase this one. So typical, I run out of room so easily. Yeah, I'll move that up there. Okay, so this might be something like z equals x squared plus y squared, or z equals x squared times y squared, or z equals 2xy cubed. Right, there's an x and a y in the right-hand side you have to do stuff to, and once you've done it, it spits out a z. So that's what we mean by a function of two variables. This is essentially a function of one variable in that if I could, I would solve it for y so that I could differentiate it I've done that implicitly, and I've been able to get this function here. This still has x's and y's in it, but this function here has two variables in it to begin with, and a third variable that sort of defines or collects the outputs of whatever it is you did to your two variables. Now let's take a really quick, do a really quick reminder of what it means to do, to take a partial derivative. What I'm going to do here is take the partial derivative of the function f with respect to x, and then over here I will take the partial derivative of the function f with respect to y. We're going to need this in the next piece of the conversation we have. So the partial derivative is just the derivative with respect to x, treating y as a constant. The partial with respect to y is taking the derivative with respect to y, treating x like a constant. So we'll do the partial with respect to x. The derivative of x squared with respect to x is 2x. And that looks just like the derivative with respect to x, let alone the partial derivative with respect to x. And it is because there's no y in this term. But if there was a y factor, then it would be slightly different, which we'll see in this next term. The derivative of this function with respect to x, if we pretend that y is some constant like 13, then we're going to get the 2 times 13, we'll pull that out front. In this case, that's 2 times some constant we are calling y, times the derivative of the x squared factor, so times 2x. There is no y prime in this. That will come into it in the next piece of the conversation, but right now I just want to remind you what a partial derivative is. Some of you haven't seen it. Some of you have, but some of you haven't seen partial derivatives before. So I know we talked about this a little bit in an earlier video, but I want to just remind you what's going on here. For the next term, the partial derivative of this function with respect to x, well, if y is a constant, then y squared is also a constant. So I'm going to have 3 times a constant squared as my constant factor, times the derivative of x, which is 1. And then in the next term, so I have just times 1 here. In the next term, I have no x's. So to take the derivative of this with respect to x, because I'm doing a partial derivative here, not implicit differentiation, but partial differentiation, I'm holding the y constant. If y is a constant, y cubed is a constant, and 6y cubed is a constant. And so the derivative of that, the partial derivative of that term with respect to x is 0. And then, of course, there are no x's in the last term either, so that's also 0. The derivative of this same function, the partial derivative of this same function with respect to y, means we're going to hold x constant. So the derivative of a constant is 0. So my very first term there, the derivative is 0. The partial derivative is 0 with respect to y. With respect to y, the derivative of this term, well, I'm doing the partial with respect to y, so I'm holding x constant. X is a constant means x squared is a constant, and 2x squared is a constant. So I'll bring that so-called constant out front, or leave it out front, and then take the derivative of y with respect to y, and that's 1. So this would be times 1. If x is a constant, I'm on the next term, then 3x is also a constant, so I'll bring that, or leave that out in front. And then the derivative with respect to y of y squared is 2y. And lastly, not quite lastly, but almost lastly, the derivative with respect to y of a term with nothing but y's in it is just the derivative with respect to y. So this is going to be 18y squared. And then the minus 7 really is a constant, so we just have a plus 0 there. And of course, I could tidy these up. I'm going to have 2x plus 4xy plus 3y squared for that one. And for this one, I'm going to have 2x squared plus 6xy plus 18y squared. So that's what we mean when we say partial differentiation, and that is different from implicit differentiation, at least in the processes that are involved, the focus with which you attack these problems. Now what I'm going to do is take a look at a a differential equation that has certain features that let us use the ideas we've just been talking about to solve it. This differential equation is not autonomous, it's not first order linear, and it's not separable. So we're going to need to find a different strategy for solving. Okay, here is a differential equation that is not separable and not autonomous and not a first order linear. What we're going to look at here is this piece of the function and this piece of the function, these two sort of sub-functions, if you will. And I'm going to make an observation. The function, this is a different function, the function in x and y called f, that function I'm going to say is 2x squared y plus x plus the sine of y. And when I take the partial derivative of this function f with respect to x and the partial derivative with respect to y, with respect to x, I get y is a constant, so I get 2y times 2x plus 1 plus 0, because y is a constant, so sine of y is a constant, right? Sine of a constant is just a number. You evaluate sine at some number, you get a number. And the derivative of that is 0. So that's with respect to x. With respect to y, now x is a constant, so 2x squared is a constant, and that's what's in front of my y, so I'm just going to get 2x squared plus 0, because x is a constant. When I'm differentiating, partial differentiation with respect to y means take x to be a constant, hold x constant. The derivative of sine with respect to y is cosine y. And now look at, well, let me tidy this up a little bit. This is equal to 4xy plus 1. And when I look at this, I see this function. And when I look at this, 2x squared plus cosine y, I see this function. So I can write this differently. I can write my differential equation 4xy plus 1 plus 2x squared plus cosine y, y prime, as partial f partial x plus partial f partial y times y prime, which we know is also written as dy dx, and that's equal to 0. So these two equations are equivalent based on the fact that these are the partial derivatives of the function f. I've had to go and find a function f that lets me do that. And that's going to be key. Finding that function is going to be key to this section. For right now, I've just given it to you so that you can see what's happening. Once I have that, once I have this equation in this form, I can rewrite this as, let's just subtract the partial f partial x from both sides first of all. That gives me partial f partial y times dy dx equals negative partial f partial x, partial. And that, then when I divide both sides by partial f partial y, I get dy dx is equal to negative partial f with respect to x over partial f with respect to y. You'll also often see different notation here, dy dx, because this gets cumbersome, right? This gets very cumbersome to write. So oftentimes you'll see, for example, f sub x and f sub y. This is the same, has the same meaning. This is the partial derivative of the function called f with respect to the variable x. And this is the partial derivative of the function called f with respect to y. And that's what this means. The partial of the function called f with respect to x, the partial of f with respect to y. Means the same thing. So sometimes you'll see this notation, and I may start using it myself. It's a lot easier to write. One of the things we have to be very careful about at this point is recognizing that y in this context, there's a y here, there's a y here, there's even a y here in this function that I found that does this for us. And that y there means there's an input variable of y after a fashion, right? This could be written as z equals 2x squared, etc. But what's important is to recognize in this context that this is not how we're using this. It's not how we're using these two variables. Y in this context, this little aside here is mostly for the benefit of students who've had Calculus 3, because this could get very confusing. In this setting, in both settings in Calculus 3, we'd say, well, f of x, y is just another variable. We call it z in some cases, or omega, or something else, right? X and y are input variables, and z is the output variable. But in this context, this function here, I suppose, has two input variables, but one of them, y, is itself a function of x. So I could write this as, wrong pen. I could write this as f of x comma y of x equals 2x squared y of x, that's a function, plus x, plus the sine of the function y of x, right? And that's important because when we get down here, we're talking about the function, the derivative of the function y with respect to x. We can only do that because y is a function of x. So because I've been able to write this derivative in this way, I can say that y prime, the derivative of, where's my pointer? This y prime right here, which I can write as dy dx, can be thought of as simply this quotient, right? Okay, let's go back a little bit to, I want to look at, I'll use a highlighter. I want to look at this expression right here. And we remember that our function y is itself a function of x. Then taking the derivative of f with respect to x and the derivative of f with respect to y, this is essentially the chain rule. This is the derivative of the function, let me write it this way, the derivative with respect to x of the function f of x and y. Because when I take the derivative of a function that's got two variables in it, one of which is defined on the other, I'm going to take the derivative of the function f with respect to x. And back on the previous screen, I showed you or reminded you what or 2 screens ago, I showed you what the implicit differentiation was. And on the previous screen, I showed you or reminded you what the partial differentiation looked like. But here I'm going to take the function f and I'm going to differentiate it first with respect to x and then with respect to y, which is also a function of x. So this expression here really just means this. And that means that this function up here, this equation up here, which is in this form, this is my partial of f with respect to x, plus, remember that's how I got this here, my partial of f with respect to y times y prime. This part here is the part that's in green. This is my green piece. This is my yellow piece. And this is not highlighted in this equation, but I can highlight it there. And it doesn't show up down here because it's already a part of what I'm aiming for. Wrong pen, sorry. It's already part of what I'm aiming for. It shows up down here. All the pieces are in place here, but what this is simply the derivative of the function f of x and y with respect to x because of the chain rule, because y is also a function of x. So that means that I can rewrite this original function here, let's do it here, as, maybe I won't do it quite there. Let's see. What I want to do is indicate that this whole thing here can be written as the derivative with respect to x of f of x, y. And of course, the right-hand side there is still 0. All right, so here's where the magic happens. If I have the derivative with respect to x of a function, f of x comma y, and that's equal to 0, and I integrate both sides, I get just f of x, y equals a constant. So once I know what that function is, the function whose derivative with respect to x gives me this piece of my differential equation, and whose same function whose derivative with respect to y, partial derivative with respect to y, gives me the other function, the piece next to the y prime, the dy dx. Once I know what that function is, then that's my solution. I mean, this is a general solution. I don't know what C is. I don't have a particular solution here. I don't have any initial conditions. But as far as solving one that looks like this is essentially your answer. F of x, y in this case is 2x squared y plus x plus the sine of y. And that's equal to a constant. So our next big question is, how do you find this function? And a sub-question to that, I would say, is, does such a function exist? Well, in this case, obviously, it does, because I gave you one to try and it worked. Well, I did it for you, but you get the idea, right? This function has the property that its partial derivative with respect to y gives me this function, and the same function's partial with respect to, with respect to x, and with respect to y gives me this function. So the first question, or a big question, is how do you find this function? And a question we might want to ask ourselves before answering that question, before trying to answering that question, is, does one exist? How would you go about finding out whether a function even exists that will satisfy this property? Let's take a look at the same function again. I've written it very small here, and I've enclosed it in this little cage because I don't want it to get too confused with what else is going on the screen here. This is my original function f of x, y that I gave you that turned out to work for this situation, for this particular problem. And I've rewritten the partial derivatives with respect to x and y, and I've used this notation here for a reason. Partly it's taking up less room, but also I want to now take the partial derivative of the function f. Having taken that partial derivative with respect to x, I now want to turn around and take it with respect to y. And then over here, I'm going to take the partial derivative of f with respect to y, which I have already done, and turn around and take it with respect to x. So I'm taking a second derivative here. I'm taking the derivative of this function, but now I'm going to take it with respect to y, right? Since x is a constant, 4x is a constant, and the derivative of that function is, with respect to y, is just 4x. And here I have taken it with respect to y once, and this is the answer that I got. Now I'm going to take the derivative of this, the partial derivative of this first derivative, but this time with respect to x. And when I do that, I'm holding y constant. So y is a constant, cosine of y is a constant. So I just need to take the derivative of this term here, and I get 4x. And notice that these two are equal. Now, this is only an example, right? I'm only using one function, and I've taken its derivative, and I've taken its derivative again, and I've shown you that they're equal. I'm doing it this way in part because at least where I teach this class, the prerequisite for this course is Calculus 2, not Calculus 3. And so I don't really want to get too far down into the weeds in the theorem. In our textbook, it's Theorem 2.6.1. I don't want to get too far down into the weeds on that because it really requires a sort of a Calculus 3 thinking scheme in order to be able to make sense of it. But it's an interesting result. And it turns out what this theorem tells me is that if the derivative of this thing, first with respect to x and then with respect to y, and the derivative of this thing first with respect to y and then with respect to x, if those two derivatives are equal, then this function exists. Now that's a little weird, but remember that the derivative of this thing with respect to x, the partial with respect to x, was already present in this problem, right? So I have a function here which, when I take its derivative with respect to y, I get 4x. And I have another function here, which when I take its derivative with respect to x, I also get 4x. So I know I'm taking the second derivative of this function, but what I'm essentially doing is testing whether these two functions have a function whose second derivative, once with x, once with y, if the second derivative of this, anyway, I'm kind of talking in circles. If you take the derivative of this function with respect to y, and this function with respect to x, and they're the same, then such a function exists that will allow us to do the rest of this problem. So that's what that theorem really is telling us. It's important that these two functions are continuous on a rectangle. I don't know that it has to be a rectangle. I don't think it has to be a rectangle on a region. If they are continuous, then these are continuous. And I'm using a very specific example here, but well, let's take a look on the next screen at another example, and I won't give you this function. We'll just test to see whether such a function exists, and then from that point we'll go on to see how we go about finding this function. All right, here are a couple of differential equations. There's a dx here and a dy here, a dx here and a dy here. I put these in this form because it's worth mentioning that they don't always come to you in the form that you need them in to do the work you need to do. So sometimes we need to manipulate them a little bit. If I divide both sides of this equation by dx, then I'm essentially dividing each term by dx. And I get x squared y minus x y squared plus y cubed y prime equals 0. And now to test whether or not there's a solution, I'm going to take the partial derivative of the first function with respect to y. This is the one that's attached to the y prime, right? So I'm going to take the partial derivative of with respect to y of x squared y, and because I'm differentiating with respect to y, x is a constant, that's just going to give me y. And the partial derivative with respect to x of x y squared plus y cubed, y is a constant, and that's going to give me y is a constant. So take differentiating with respect to x, I have a constant times x, that's y squared, plus, well, if x is my variable differentiation, y is a constant, this whole thing is a constant, that's going to be 0. These are different. So I cannot solve this differential equation using this technique. It's not an option. Sometimes there are other techniques that you can employ and still solve the thing, but in this case, this is not an exact differential equation. So I can't use the technique from this section for this problem. Okay, let's take a look at the other one. I need to do the same thing here. I need to divide each term by dx. As it happens, you can see that in this form, in the original form, it's also going to turn out to be easy to put it into the form that we're now used to seeing it in. So it's not necessarily a strict requirement that you do this step, but I like to do it just because I'm more comfortable with the equation being in the form that we've been talking about. So what I'm going to have here to work with is 1 plus the natural log of x y plus, that's times 1, plus x over y, y prime equals 0. And I'm going to think of this, well, I guess I'll get to that in a minute. So to test this, I want to take the derivative of this function with respect to y, and this one, partial derivatives, not implicit, with respect to x. So the partial derivative with respect to y of 1 plus the natural log of xy is the differentiating with respect to y, so x is a constant. This is going to be 0 anyway, plus the derivative of the natural log is 1 over the argument, but then I need to use the chain rule and take the derivative of the inside function. And I'm differentiating with respect to y, so x is a constant. It's like saying 3y. Differentiate 3y with respect to y, you're going to get 3. So I'm just going to get x. And when I tidy that up, I get 1 over y. For the other function, I'm going to think of this as x times y to the negative 1. So I have the derivative, keep writing d when I need to write partial, the derivative with respect to x this time of x times y to the negative 1, and that is with respect to x, y is a constant. So if y was 3, this would be 1/3, right? And differentiating with respect to x, I'm going to get just that constant. It's x to the first power. So I'm going to get y to the negative 1, which is 1 over y. And these are the same, right? We have 1 over y and 1 over y. In the previous problem, we got y and y squared, which are not the same. So that is not an exact equation. This test, because these two results are the same, tells me that this is an exact equation, an exact differential equation, and I'll be able to solve it using the techniques in this section. I really wanted to use the same equation that I had used in the previous screen where I showed you that not all differential equations are exact differential equations. The first one turned out not to be an exact differential equation. The second one turned out to be exact, and I wanted to use that same differential equation here to show you how to find the solution, but it turned out to be really very messy. So I'm going to go with a simpler one. This one here is almost in the form that we're used to. You can also take it straight from this form if you prefer. I'm going to highlight a couple things here. I'm going to make that, factor that term and sorry, not factor it, highlight it and highlight that term. If I divided through everything through by dx here, I would get 2x e to the y plus x squared e to the y plus cosine y times dy dx, which you can write as dy dx, or you can write it as y prime, equals 0 divided by dx, and so I get 0. And again, if I just highlight those, I didn't really mean to highlight my dx in the line above. If I try to erase it now, let me see if I can erase it. It erases the dx as well. That's okay, I'll write that back in. Those are the functions that come about, we hope, when we find a function whose partial derivative with respect to x is this function, and whose partial derivative with respect to y is this function, we hope there is a function, and then these are the functions that come out of that. So how do we determine what that function is? Well, let's first make sure there is a function, because if there isn't one, then we'll be wasting a lot of time. And the way we do that is to take the partial derivative of, oh, my pen's not working again. Come on. Sometimes it just needs to take a break, I think. We want this to be the derivative of some function, partial derivative with respect to x. But what we're going to do is take what would have been the second partial derivative of that function, the function we're looking for, with respect to y. And in order to do that, all we need to do is assume that this is already the first partial with respect to x, and take the partial with respect to y of that function. And we'll do the same thing over here. we're assuming that this is, or we're hoping that this is the first partial derivative of some function with respect to y. So we're going to take the partial derivative with respect to x of that function, and that will give us, if the function we're looking for exists, what would be the second partial derivative of the original function, the one whose first partial was this function and whose second partial we're about to work out. Okay, so let's do this. The partial derivative of this function with respect to y, well, with respect to y, 2x is a constant. So what we have here is a product, and the derivative of a product is the first times the derivative of the second. Well, that's e to the y, and the derivative with respect to y of e to the y is e to the y. Plus the second, e to the y, times the derivative of the first. But with respect to y, that's a constant, so that's 0. So there's my second partial derivative, or my partial derivative of this first function with respect to y. On the other side, we have, we're going to take the derivative of this function with respect to x. And again, here we have a product, so I'm going to have the first times the derivative of the second. Well, the derivative of the second here, the second function is e to the y. Well, that's a constant, because e is a constant and y is a constant, and e raised to a constant is a constant. So that's going to be the derivative of a constant, which is 0. So that's my first times the derivative of the second. Now I need the second, which is e to the y, times the derivative of the first. Now I'm differentiating partially with respect to x here, so the derivative here is going to be 2x. Plus the derivative of cosine y with respect to x, partially, y is a constant, so cosine of y will also be a constant, so its derivative will be 0. So I end up here also with 2x e to the y. And because this function is the same as this function, I know that this is an exact differential equation, and I can use the technique I'm about to show you to find out what the function is that satisfies the characteristic that its first partial with respect to x is this function and its first partial with respect to y is this function. I want to take just a second here and label some things. Your textbook, and actually several textbooks, use the notation m for the function that comes about by taking the partial derivative of some other function with respect to x. That's really a mouthful. I just don't know how else to say it. This function right here, they call it m, and this one here, the one that is the derivative of some function with respect to y, they call that one n. I'm not sure how they came. Those letters came to be conventional for this, but they seem to be fairly ubiquitous. It does make it easier to refer to these. If I talk about function m now, you'll know which one I'm talking about and which one is n. Right, so how do we go about finding out what function it is whose first partial with x is m and whose first partial on y is n? How do we find that? Well, how do you find any function if you know its derivative? I'm going to guess that you are probably inclined to integrate. So if I know that the derivative of a function, wrong pen, there we go, that the derivative of a function is 2x e to the y, and that's the derivative that I got when I partially differentiated with respect to x, then I'm going to integrate it with respect to x to find out what function gave me that derivative. And the same is true of the other one. What function has a derivative of x squared e to the y plus cosine of y? Well, that one was differentiated with respect to y, so I'll integrate it with respect to y. The first one, since I'm integrating with respect to x, anything with a y in it, or anything that's defined exclusively on y, is a constant. So 2 is a constant and e to the y is a constant, so I can bring those out front. So I have 2 e to the y times the integral of x dx. and that's 2 e to the y times x squared over 2. The 2's cancel, and I get e to the y x squared, or x squared e to the y, plus a constant, right? Now, it's not a constant, but I'm going to come back to that. I don't want to confuse things too much right now. We'll just say for the moment that it's a constant. On the other side, we have a function whose derivative is x squared e to the y plus cosine of y, and I'm going to do this one first by splitting it up. If I can actually do this, dy plus the integral of cosine of y, dy. And this looks like it's going to need to be done by integration by parts because I have a product here. But I don't really, I certainly don't need to do integration by parts because in terms of y, x is a constant. So x squared is a constant. So I can write this as x squared, the integral of e to the y dy, plus the integral of cosine y dy. And we know that the integral of the exponential is just the exponential. And we know that did I say derivative? I meant integral. And the integral of cosine is sine. And these are both with respect to y. I'll call this C1 and this one C2. So I've done my integration. And what I want to highlight now is that if I were to differentiate this expression, I should get this expression. And if I were to differentiate this one with respect to y specifically, then I should get this integrand. I should get this expression. The thing is, I could integrate this with respect to x, and this might be a constant, but it might be a whole function in terms of y, right? I've integrated with respect to x. When I differentiate with respect to x, anything that contains only y's would go to 0. We would treat it as a constant, and it would go to 0. So this could actually be, I'm waiting for my pen to change, this could actually be, I'm going to call it a of y, a function called a in terms of y, right? Y is my variable. Equally, on the other side, when I differentiate this with respect to x, I've integrated, with respect to y, I've integrated with respect to y. When I differentiate with respect to y, as long as this only has x's in it, no y's, then it will differentiate to 0 just like a constant would. So I can change this one to some constant, some function that only has x's in it, okay? Now what we're trying to do is we're trying to find a function whose first derivative on x gives me this, and whose first derivative, partial derivative on y gives me this. And what I've found so far is a function which when I integrate with respect to x gives me what I want, and a different function, or a potentially different function, which when I differentiate on y gives me what I want, but they have to be the same. The function I end up using has to be the same. So I need whatever this function is, including this unknown piece here, I need for its first derivative with respect to x, its first partial with respect to x to give me this, but I also need for its first partial with respect to y to give me this function here. In other words, I need the partial with respect to y of x squared e to the y plus a of y to equal x squared e to the y plus cosine of y. I also need, well, let me go back. I also have here a function, because of the way I've defined it, whose first partial with respect to y gives me this, but I also need it to be a function whose first partial with respect to x will give me 2x e to the y. I need both of those to be true. So let's take this partial derivative, and it's already set equal to this expression, and let's just see what happens. The partial with respect to y of this first term here, since we're integrating with respect to y, differentiating with respect to y, x is a constant. The derivative of e to the y is e to the y. So I just have x squared e to the y. I'm going to go up here. X squared e to the y plus, now I'm differentiating this function here partially with respect to y. Well, I don't know what it is, so I can't really differentiate it, but I can write it as a prime of y. And that is equal to x squared e to the y plus the cosine of y. And note that I have an x squared e to the y plus stuff equals x squared e to the y plus stuff. And so term by term, if these are to be equal, then a prime of y must be equal to the cosine of y. Now both sides of this equation are in terms of y, so I can integrate both sides. If I take the integral of this side dy and this side dy, I get that a of y is equal to the sine of y plus a constant. Now this time I really am using a constant because this equation, or this derivative here, is in terms of y, and this answer, this right-hand side, is also in terms of y. There are no other functions, there are no x's, right? I've narrowed it down to only dealing with y. So this really is a constant, and I'm going to call it C1 because I will probably have another constant on the other side. So now I know what my function a of y should be. All right, let's go figure out what b of y is. Well, the left-hand side, I'll go up here, is asking me to take the partial with respect to x, which means anything with a y in it is a constant. That e to the y is a constant. So I'm going to have 2xy e to the y. That's, let's see, where's my pointer? The first times the derivative of the second. Well, the derivative of this is going to be 0. Plus the second e to the y times the derivative of the first. And that's 2x, and that extra y should not be in there. So 2x e to the y. That's the first term. I have the first times the derivative of the second plus the second times the derivative of the first. The second term is the sine of y, but with respect to x, which is how I'm differentiating, that's 0. And with respect to x, the derivative of b of x is b prime of x. I have plus b prime of x. And that has to equal 2x e to the y. Well, guess what? I have, let me use my highlighter, I have a 2x e to the y here and a 2x e to the y here. So that means that term by term, b prime of x has to equal whatever's left on the other side, which is 0. And when I integrate that, it's all in terms of x. So I'm going to get the integral symbols here, I guess. dx. b of x is just some constant. Constant 2. So now I can go back and give myself a little bit of writing room here. Where did I put that one? There it is. And I'll do some highlighting. Let's go with yellow for this function here, because that's the stuff that's coming from this m function, from my left function. My right function, my n function, has been in green, and I had it except for this b of x thing. So now I know what a of y is, and so this function is going to be x squared e to the y plus a of y, which is sine of y plus a constant. Now this one is going to be x squared plus e to the y, times e to the y, times e to the y plus sine of y plus a constant. How do you like that? So now, since I have my function, it's x squared e to the y plus the sine of y plus a constant. I have it here, and I have it here. Where'd it go? It's the same function. And so when I use this function, it doesn't really matter, because they're the same function, it doesn't really matter what c is. So now I'm just going to call it c. And I'm going to say that my function is x squared e to the y plus the sine of y plus a constant. Now, This is not an equation, right? Normally we would write a function like this. We would say y equals 3x squared minus the square root of x plus 7, or something like that, right? We have all our x stuff on this side, and we define y as being stuff you do to x. For one x value, you're going to do these things and get one y value out. If you choose a different x values, you're going to do the same things to x, but you're going to get a different y value out. And that's how we define a function. But notice the equal sign. Y is dependent on x here. Y is not dependent on x here, nor x on y, although we could in this case write it as, x equals the square root of, or the negative square root. Anyway, we could solve this one for x in terms of y. But in general, conventionally, what we do is we just say that this thing is equal to 0. That gives us the equal sign, right? It makes it into an equation. We have an expression, then we have a relationship defined between x and y. And so all that's really left now is a little bit of convention. And what that convention is in this case is that we generally don't put this plus c here on the same side as the expressions of x and y. We're just going to subtract it from both sides. Of course, when I subtract that from both sides, I get x squared e to the y plus sine of y equals negative c, but c is just a constant. So I can just say that x squared e to the y plus sine of y equals c, and that's my solution. So let me highlight that. That's our final step in this process. Now, there's more to this section. What we've learned in this video is what an exact differential equation is, what class of differential equations those are, what they look like. We've learned how to determine whether a given differential equation is exact, whether it satisfies the criteria for being an exact differential equation. And we've learned how to solve an exact differential equation. Now, I've only done one example. If I have time, I'll add some more examples to another video. But for now, I'm going to stop this video, and I'm going to start a new one that deals with situations where the equation that you're given is not exact, but you can make it exact with something called an integrating factor. We've seen integrating factors before, earlier in the quarter, but we're going to use them again in this new context. So that's it for this one, and look for the second half of this section in the next video.